In this video, we're going to look at how to sketch the graphs of sine and cosine. We'll start by looking at how each term of the graph impacts its overall shape, and then we'll go through some of the key examples of how to sketch them by hand. For those who don't know me, my name is Chris Sinazoni. I've been tutoring for about 2 years now, and I make these videos so that VCE students can do the best they can in math methods. With that out of the way, let's get into it. Without any transformations, the graphs of sine and cosine look like this. We can immediately identify some similarities between the two. The first is that they both look like waves. They both have peaks, they both have troughs. And the second is that they repeat their wave-like pattern within 2 pi. In fact, the only true difference between sine and cosine are the starting locations. Sine will start at the origin and then immediately trend upwards, whereas cosine will start at a peak and then immediately trend downwards. Other than that, these graphs are identical. The A term is a dilation factor from the x. It's responsible for stretching the graph vertically. In the context of circular functions, this tells you how far the peaks and troughs are going to be from the middle line. Normally, the peaks and troughs occur at plus minus 1. But if you were to have a multiplication of 3 out the front, suddenly those peaks and troughs are now going to occur at plus minus 3. The A term is often used in determining the amplitude of your circular function, where the amplitude is defined as the difference between the peak and the mid-level of your circular function. So, I want to make this clear. This specific definition of the amplitude means that it's never possible for the amplitude to be negative. So even if you had a negative 3 at the front of your circular function, its amplitude would still be 3. We will explore later on in the video what the negative sign actually does, but you need to be aware that amplitude can only ever be positive. The n term is very similar. It works in the opposite direction to A. As n gets larger, the graph compresses. As n gets smaller, the graph extends. The main takeaway here is that the n term is responsible for telling you how long it'll take the circular function to repeat its pattern once. And this quantity in particular is called the period. It's calculated by 2 pi divided by n. So, for example, if we had sine of 2x, then n would be 2, and hence the period would therefore be pi, after you simplify everything down. And sure enough, that's exactly how long it takes for the graph to repeat once. In the case of cosine x over 2, you now have an n term of a half, which after simplifying will give you a period of 4 pi. And sure enough, that's what we see. Okay, so there's a few more terms to look at, but for now, let's take a break from learning those new terms and just look at how to sketch graphs that only have a and n in them. This is the simplest kind of graph that you have, and it's also the most common that will come up, at least as far as the textbooks are concerned. Under these circumstances, we follow this framework. Let's give it a shot. First up, we want to find the period and the amplitude of our circular function. The period is calculated by 2 pi over n, and so the period of this circular function must therefore be 2 pi over 3, because n is 3. We can also see that the amplitude is 2 because the a term is 2. That means that our peaks and troughs are going to occur at plus minus 2. From there, we need to figure out what the x-coordinates are of all of our key features. These kinds of graphs always start at the origin and end at the period. So in our case, it means we're going to start at 0 and end at 2 pi over 3, at least as far as x is concerned. From here, all you're going to do is halve this interval twice and then fill in that 3/4 mark to make sure that everything is evenly spread, which simply means adding the first interval to the second interval. When you do that, you'll find that everything along that interval is evenly spread out. What we do from here is try to figure out the y-coordinates at those spots. And we do that by referring to the generic version of the cosine, which we know starts at a peak. Hence, our first coordinate is going to be 0, 2, since 2 was the value of our peak. From there, it will fall to a mid-level, then a trough, then go back up to the mid, and then finally conclude at the peak. All you do now is join the curve connecting all of those dots that you plotted out earlier. Now, if you find it difficult to plot those dots out just by referring to the generic cosine, then you can always just sub in different x values into your cosine to get the same shape overall. So let's say you forget where cosine starts. Well, if you want to know where it starts, you're just going to sub in x equals 0 into your function. And when you simplify that, you will get y equals 2, which we found earlier by just looking at where the key features should have been. So it's a decent fallback for at least getting an idea of what the graph should look like. I wouldn't be doing that for every point along the curve though. It takes a bit of time. So to summarize, this way of sketching the circular function works only if you have just a and n in your graph. There are more terms to have a look at, so let's dig a little bit deeper. Reflections are identified by negative signs, either attached directly to your circular function or specifically just on the x term. Reflections about the x-axis are those where the negative sign is applied directly to the circular function, whereas reflections about the y-axis are those where the negative sign is applied directly to the x. Now, for context, when it comes to sketching circular functions, there will never be a negative sign attached to the x variable. For whatever reason, that just doesn't show up at all. So this video is only going to focus on reflections about the x-axis, which in basic terms only swaps the location of the peaks and troughs. All your peaks become troughs, all your troughs becomes peaks. That's it. Horizontal translations are determined by the h term. If you have x minus h, then you're shifting your graph to the right by h. So, for example, if you had x minus pi over 3, then you would be shifting all of your key features to the right by 3. If you have x plus h, then you have a shift to the left. So, for example, if I had x plus pi over 3, then we're going left by pi over 3. Before we move on, I want to highlight that when you have horizontal translations, your y-intercept isn't guaranteed to be one of your key features, peak, trough, or mid. So, under certain circumstances, you might have to solve that individually. All you do here is sub in x equals 0. Alright, well, we've increased the complexity. Let's make sure we can still sketch these by hand. The only major thing that changes when it comes to the previous framework is that all we're going to do is take those earlier coordinates we found and then just shift everything horizontally. So, from the top, we have a period of 2 pi since n was 1, and we have peaks and troughs that occur at plus minus 3 since our amplitude is 3. We also notice a shift to the right by pi over 2. So we're going to keep that in mind later on when it comes to filling out our x coordinates. But for now, we're just going to set up the interval. So once again, you start from 0, end at the period, halve that interval twice, and then fill in the remaining spot. Now we're going to adjust those spots forward by pi over 2, since that's our horizontal translation. All that means is that you add pi over 2 to all of those values. Other than that, everything else continues as normal. This time we have sine, which we know starts at the middle. Hence our first coordinate is now going to be pi over 2, 0, since pi over 2 is the new starting point of the circular function. Sine will then move to a peak, then a middle, then a trough, and then finish up again at the middle. Quick thing worth mentioning, your graph isn't guaranteed to have a y-intercept. This one doesn't because it was shifted to the right, and the domain cut it off too early for it to have a y-intercept. But if you do need to find your y-intercept, you're just going to sub in x equals 0 into your circular function, and that will give you the y value that you need. Anyway, all we do from here is finish the curve by connecting all those dots. The last complication are vertical translations. Vertical translations are determined by the c term. If you have plus c, then your graph is shifting up by c. So, for example, if you have plus 2 at the end, then that means that your graph is shifting up by 2. Notice how now the middle occurs at y equals 2 instead of y equals 0. And your peaks and troughs are still plus minus 1 separated from that middle. So a peak of 3 and a trough of 1. If you instead had minus c, then your graph would move down. In this case, we have minus a half, and so the graph is shifted down by a half. Again, you see that y equals negative a half becomes the new mid-level of that circular function. One major issue with vertical translations is that your x-intercepts no longer coincide with the mid-level of your circular function. We now have to solve those individually. Let's have a look. Okay, let's go through it. The only thing that changes here is that we have to solve our x-intercepts at the end. Let's try it. First up, we want to find the period and the amplitude. The period is going to be 2 pi since n is 1, and the amplitude is going to be 2 since a is 2. Now here's the slight difference. When you have a vertical translation of 1, it means that your peaks and troughs are now going to be shifted up by 1. So instead of having them at plus minus 2, we now have them at positive 3 and negative 1. From there, we're still going to find the x-coordinates of those key features. So we put the period at the end, halve it twice, and then fill in the remaining spot. We have no horizontal translation, so we can just leave those there as they are. Now, we're just going to find our y-coordinates at those spots. Cos normally starts at a peak, so we would expect it to start at positive 3. However, we have negative cos, which means it's going to reflect down to the trough, which occurs at y equals negative 1. Otherwise, the pattern continues as normal. We go from trough to mid-level to peak to mid-level back down to trough. From here, we're just going to draw our curve connecting those dots. all that's left to do now is find the axes-intercepts and the endpoints. The y-intercept is found by summing in x equals 0. The good news is we don't necessarily have to do this. We already know the y value at x equals 0, so we're going to skip this. From here, we're just going to tidy things up by solving for our x-intercepts. This is just like solving a circular function where y equals 0. So let's give that a shot. So we're just going to start by getting our exact value expression, which means getting the cosine on one side and an exact value on the other. In this case, it just means subtracting 1 from both sides and then dividing both sides by -2. This graph isn't a composite function, so we can skip step 2. From here, we're just going to figure out where does cosine equal a half, and that's going to occur at pi over 3 and 5 pi over 3. Just like that, job's done. Those solutions that we found became the x-intercepts of our graph. The good news is this is as hard as it's going to get. This question specifically was pulled from the 2018 exam, and it was split across 2 questions totaling 5 marks. Furthermore, this is literally the only example I can find of having to sketch a circular function by hand in a tech-free exam. So this kind of question is very rare in general, at least as far as the exam goes. There's still a couple of reasons why we're going into such detail as to how to solve each individual type of question, and that's simply because SACs are moderated by the schools. They are self-contained topics, and they can be as complicated or as simple as the school thinks they should be, whether or not the exam is as easy or as hard as the SAC. And the other reason is that you still need to be able to interpret the graphs of circular functions even if you don't have to sketch them by hand, and that will become necessary in the Tech Active exam. If you found this video helpful, then you should consider joining my free community. I host a Q&A call every week to personally help you through any of your specific questions, and you'll also get access to more resources like this, including written and recorded lecture content, as well as practice exams and SACs with detailed solutions. It's pretty cool, you should check it out. I'll see you there.